Welcome back. This is the second part of this course. We will now look at how we record NMR spectrum, how we analyze the 1D spectrum. So, this is just a brief quick look at the chemical shifts. So, this is what is shown here, that in a given molecule, let us say we take example of ethanol, we saw that the different hydrogen atoms, they are having different energies because they are different chemical shift value, that is coming because of the electron density around these hydrogens, they are different compared to each other, and this difference in that energy the electron density translates or results in the difference in the different energy levels. Remember, omega is gamma b 0. So, if the b value changes, the omega changes, and that is converted into a chemical shift which is shown here. This is schematic drawing here of ethanol, but let us look at mathematically what we saw, that if this is how we calculate the chemical shift value, that when you have an omega, let us take some reference compound, as reference can be any particular compound, we will see that later, and the reference we assume, remember, it is an assumption, we force it to having a 0 chemical shift. That means the sigma value we will say for the reference molecule, let us say is 0. In that case, that omega of that reference is gamma b 0. But in reality, in for other the actual molecule what we are looking at, there the sigma we cannot consider as 0, because that has some finite sigma value with respect to the reference, and that is why this effective magnetic field around that nucleus is not gamma b 0, but it is reduced because of this sigma. So, this is the shielding effect, shielding factor. So, now if I do this math, what I will do is I will subtract these two and then rearrange the equation to get the sigma. So, this is what is shown here, and you can see here now based on this how we get this the chemical shift. So, if I take that the chemical shift of the reference, of course reference in terms of the difference of the bit from the reference divided by gamma b 0. So, what basically chemical shifts are always calculated by taking the difference between your molecule, the hydrogen which you are looking at, from the reference hydrogen, and then divided by the main magnetic field value, which is what is in megahertz. So, if you do that calculation, because V reference is in megahertz, we basically get the value in megahertz. So, that is why it is if you take the denominator as 10 to the power 6 and it becomes 10 to the power minus 6 when it comes to numerator, and therefore, we use the word million, parts per millions. 10 to the power 6 is million, it is per million. So, the sigma values typically what we get is in parts per million. So, this is how a chemical shifts are calculated. In a nutshell, it basically means you take a reference compound, call it as a 0 frequency, 0 chemical shift, and take the difference of that from that peak from any other peak, and that frequency is converted into this sigma value by dividing it by the main magnetic field, and that is how we get the ppm value. So, this is what it means is this is something we saw again in the last few slide classes, that the chemical shift value does not change with field strength. That is because we have taken care by dividing it by the magnetic field. So, in some other magnetic field, it will basically be if 600 megahertz, this will be 600 megahertz, if it is 700 it will be 700, but because the frequencies are also scaled according to the chemical shift, this omega also depends on the frequency on b 0, the b 0 and b 0 effect cancel out, and essentially it becomes independent of the magnetic field. This also we saw in the previous class. Now, let us see how we actually experimentally record the NMR data. What are the practical aspects? This will be useful if you are setting up an NMR experiment on an NMR spectrometer, and therefore, you should know what are the different parameters involved and how a spectrum depends. In NMR spectroscopy, one thing one has to understand is very critically dependent on the parameters. So, these days many of the spectrometers which are commercially available, they have all these parameters set by default. So, many of the users, many of the people, students and users who record NMR spectrum, they never actually get to see these values, they never get a feel of these values, because they are all set by default. But as an NMR expert or a spectroscopist, if you want to understand spectroscopy in more detail and actually use it in your research, it is very important that you understand the different parameters which are used in setting up an NMR experiment. So, we are not going to go in details of this, we are only going to look at a few practical values, practical parameters which are very important, because if a wrong value of this delay, suppose somebody comes and changes this value, and the default value changes, it may give a completely bad spectrum, and you may think the sample is a problem. You may think that something happened to the spectrometer, but actually what would have happened is that simply the delay value suddenly got changed because of some missetting or miscalibration, and that resulted in a bad spectrum. So, therefore, to interpret NMR spectrum also one has to know how the spectrum was recorded, how it was acquired, and that is where the practical aspects helps to know. So, these are in NMR experiment typically we use the word pulse sequence. So, we will use this word more often. So, what is a pulse sequence? A pulse sequence is nothing but a sequence of pulses. So, if you now as we go further into NMR details like 1D NMR, or if you go to 2D NMR, you will see that it is not limited to one pulse. So, if you see in the last class we mentioned that a single pulse is what is applied, and that is called 90-degree pulse, or we call it as 180 and so on. But in reality other than 1D, a simple 1D NMR, if you go to more complicated experiments, you apply a series of pulses, means series of RF radiations, very burst quick pulses which are microsecond typically long, and there are series one after the other. We also use the word train of pulses. So, this train of pulses are applied in a particular sequence. We do not apply it arbitrarily. It is not a random sequence. It is well defined way depending on what experiment you want to do. And between any two pulses there is a gap, and that gap is called as a delay, and gap is typically a short gap. It could be a millisecond long gap, it could be a few microseconds, and depending on again lot of different experiments. But always remember there is always a gap between two pulses, and that is called a delay. So, basically NMR experiment is nothing but a series of RF pulses interspersed with delays. So, you have a pulse, delay, or delay, pulse and so on. So, these are basically how NMR experiments are performed. You applied a series of pulse and a delay in between, and after the last pulse is over, that is after the final delay in the pulse program, in the sequence, then you start recording the signal. And remember we saw that is called FID. So, the FID is which is recorded the sample is essentially after the last pulse in the sequence. Okay. So, pulse sequence therefore is like a blueprint. So, let us say you want to construct a building, you give a blueprint to the architect, or the architect gives a blueprint or to the contractor starts building, and essentially he needs a blueprint, he needs how this particular experiment has to be performed. And so, a pulse sequence is telling an NMR expert basically that is how the experiment is performed, and the results what you get all depends on how this pulse sequence was constructed. So, for as you go into more advanced level NMR spectroscopy, this pulse sequence becomes more and more complicated. So, in this particular course we are going to restrict to only a simple 1D experiment and a few 2D experiments. So, if you will see that in 2D experiment already the pulse sequence starts getting more complicated, but let us start from a simple 1D NMR experiment, what the pulse sequence looks like. So, it looks like this. So, you have basically a pulse, an excitation pulse, a pulse is there, and you apply, let us say, a 90-degree pulse. When you apply a pulse, immediately after the pulse the signal starts coming, the relaxation starts. Remember this is what we saw in the previous class, and that is how we detect the signals. But what happens before the pulse? Before the pulse we use the word preparation. Preparation is basically preparing the sample. So, as soon as you put the sample in the magnet in the spectrometer, you will have to wait for some duration, and that duration is called as preparation delay. That is, you want to establish an equilibrium situation. Remember again, according to the Boltzmann law, the populations have to be distributed between the ground state and the upper state, but that does before you apply the magnetic field, that is not the case. The population, there is no energy difference of the two states, and they are all degenerate and populations are randomly oriented. But when the moment you apply a magnetic field, you need to wait for some time for this population to be redistributed between the two states. That is the preparation period. Once that happens, the system is in equilibrium, you apply a pulse, that is called excitation. So, the molecules get excited and they go to the non-equilibrium excited state, and they start coming back because of relaxation, and during that period you acquire or you capture the signal in the form of FID, free induction decay. Once that is over, you need to sometime go back to do the experiment. So, this is what is shown here. We will look at the times in little more in a few seconds. Let us look at this picture first. So, we have a preparation period, we also use the word relaxation delay. So, this you apply a pulse and then you have the signal which is called FID. Then once the FID is over, we need to go back to this position, again wait for this preparation delay, relaxation delay, and again repeat this whole sequence. So, this is how a 1D NMR experiment is done, by repeating a number of times this particular sequence. That is why we use the word pulse sequence. This is the sequence of delays and pulses. You have first a simple relaxation delay, then you apply excitation pulse. This is now a 90-degree pulse, then you record the signal, then again you go back. So, this is called, when you say number of scans. So, this is what the word we use when we go back and do repeat this n number of time. Each time the FID is stored and added together. So, this is the cycle is called a scan. So, if you do this cycle n number of times, we use the word n scans. So, now let us look at the values of these delays. So, typically this relaxation delay is of the order of seconds, and this depends on the T1 of the sample of the molecule. So, if you know a T1, so many times of course you may not know the T1 of your sample. Let us say that you have a rough estimate, because based on the molecular size one can roughly estimate the T1 values. So, typically for small molecules it will be of the order of few seconds, 1 or 2 seconds. So, you have to wait about 3 to 4 times the value of the T1. So, therefore, suppose let us say your T1 of your sample is 1 second, then you will have to wait about 3 to 4 seconds, or ideally they say 5 times the T1. So, 5 times the T1 is 5 seconds. Practically typically we wait about 3 times the T1. So, about 3 to 5 seconds you wait for that particular sample, then you apply this pulse, and this pulse, remember, is a very short duration, a few microseconds. So, this is called RF pulse, a burst of RF, and after this few microseconds are over, this magnetization would now be in the y axis or x axis depending on the direction of the pulse, and this is what we saw in the last class, how the excitation brings the magnetization to the xy direction. Now, once you remove the pulse, the magnetization goes back towards z axis and it dephases in the xy plane, and that is what we called as T1 and T2 relaxation. And during this time when it is in the xy direction, it starts dephasing. The dephasing is what is captured as a signal decay, is what is we can see here, and the oscillation, the magnetization is rotating and going back to z axis, that is the oscillation is coming because of the chemical shift, and that is captured as a frequency of this wave. So, this is FID, what is stored in the computer, but if you do it n number of times, a repetition, and each time it is added together. So, suppose you record 10 times, the signal is added 10 times. And why do you record it so many times? The reason is to get better signal to noise ratio. So, if you remember in what happens is, in a noise, the noise is random white noise. So, the noise starts cancelling when each time you add each other, but it does not cancel to 0, it adds up slower than the signal. So, signal if it is x and you multiply 10 times, repeat 10 times, the signal will become 10x, 10 times x. So, but the noise does not go as 10 times noise, it goes as square root of 10 times noise. So, it will go as square root of 10. So, when you take a signal to noise, you are basically dividing 10 by square root of 10. So, your signal to noise has gone up 10 by 10 square root of 10, which is roughly 3 times. So, if I repeat in my experiment 10 times, my signal to noise goes up a factor of roughly 3 times. So, this is what is the idea behind repeating this experiment n number of times, and therefore, we use the word scans. So, how many scans was the spectrum recorded? This is typically the questions you will ask for practically, and that depends on their sample sensitivity. So, depends on how good your sample is. If your sample is very high in sensitivity, in concentration, and so other factors, you do not need very high number of scans. But if your sample, let us say, very dilute, and dilute sample, or if you have very less amount of samples, so you cannot make a very concentrated sample, then you have to use more number of scans, because your signal to noise has to be increased. So, this is typically the process we saw in the NMR, that you apply a radio frequency pulse to a sample and then you record and acquire, or this is physically acquiring a spectrum, I mean FID in the time domain, and upon Fourier transform you get a spectrum. So, We looked at this number of scans. So, scans basically means what is the signal to noise, the sensitivity. So, this is where we have to keep in mind what are the factors which determine the sensitivity of a NMR spectrum or experiment. So, this is what is a general list is given here. So, we can see that the first most important thing is the concentration of the sample. So, signal to noise increases linearly with concentration. So, suppose I have a 10 millimolar sample of my molecule and I record with a 20 millimolar sample another spectrum. So, the 20 millimolar sample will be 2 times the sensitivity or signal to noise compared to the 10 millimolar, provided all other conditions are kept same. So, that means you should we are comparing with the same spectrometer, same number of scans, same temperature, etc., etc. If you keep all these parameters same, then the sample concentration is directly proportional to the signal to noise. So, that means if you double the concentration, your signal to noise will go up. So, what is the typical concentration that people should use in NMR is typically about a millimolar or so. Again depends on a spectrometer frequency, depend on the type of sample. For large molecules you need more concentration because large molecules are less sensitive, we will see that as we go on. So, sample concentration is important parameter and for sensitivity. Temperature is another parameter. So, whether temperature can increase or decrease. So, what happens is if you look at theory in a theoretical way, if you remember the Boltzmann law, the Boltzmann law says that if you increase the temperature, the population between the upper and the ground state, the difference will reduce, which means that more and more molecules will now be in the upper state relative to ground state. If this comes from the Boltzmann law, I would suggest you to look at the Boltzmann law again and figure it out from there, how the temperature determines the population ratio. So, if you let us say you go to highest infinity, temperature is very high, then the population will be equal between the two states. So, remember when population is equal, the upper and lower state, the difference is 0, then you do not get any NMR spectrum. Similarly, if you go to the other extreme, let us say we go to 0 Kelvin, absolute 0, in that situation there will be all the spins will be in the ground state, nothing will be in the upper state. So, that is the maximum sensitivity, but this is all theoretical limits. Practically you will not go at that extreme temperatures because your sample will anyway not be stable. So, typically we do not go below the freezing point, we look at the solution. So, for if you take a water sample, your typical water sample will be you will not go below the freezing temperature, which is 0 degrees Celsius. So, so typically operating temperature is somewhere from 5 degrees Celsius to let us say 40 degrees Celsius depending on your sample. So, in that under those range of temperature, the signal to noise can increase or decrease. So, there is no particular reason because it depends on the molecular structure and so on. So, if you increase the temperature, sometimes it improves because it can now there are a variety of factors, we will go into that later. The T2 value increases, and if T2 increases at high temperature, the lines are very sharp, and if the lines are very sharp, the signal to noise is good. Remember we saw in the last class that the line width, that is the width of the line, depends on the T2 value. So, temperature can increase or decrease, again is sample specific, but theoretically in theory if you go down in lower in temperature, we saw the population difference but improves and it can increase, but practically it may depend on other factors also. So, now let us look at magnetic field, and here it is very clear that the magnetic field the signal to noise directly increases based on this factor B to the power 3 by 2. So, this is very important because if you go from a 500 megahertz to let us say 1 gigahertz, 1000 megahertz, the signal to noise will go more than double, it will go by this factor. So, therefore, it is very important to increase the sensitivity, you have to go to higher and higher magnetic fields. And a very important parameter of the sensitivity is depending on the type of nucleus, because remember again in the Boltzmann law we saw that it depends on the gamma value. Okay. So, gamma of a nucleus. So, if you have a hydrogen which is the highest gamma, you will have the highest sensitivity, whereas if you go to carbon, gamma is low. Similarly, the detection sensitivity also depends on the gamma value, how sensitive is the detection, and that also depends on omega, and omega depends on gamma. So, gamma is very important parameters. So, therefore, one has to be careful when you are looking at, you can't expect a hydrogen spectrum to be as sensitive as carbon because of the lower, similarly nitrogen and so on. Remember there is one more parameter which is the natural abundance. which is not listed in this particular list, and that what is natural abundance is that particular isotope, how abundant is it. So, in case of hydrogen the abundance is 100%, but in case of carbon the abundance is only 1%. So, carbon is already 100 times weaker compared to carbon is 100 times weaker compared to proton because of the abundance. On top of that, on further, this gamma value also adds to the reduction in sensitivity of carbon. So, there is a carbon to proton, remember ratio, the proton to carbon gyromagnetic ratio is 4. So, carbon is 4 times less gamma value compared to proton. So, carbon will be 4 times, in fact it is, if you detect carbon and observe carbon, it is about 16 times less. So, these parameters natural abundance and gamma further contribute to the signal to noise. So, signal to noise increases with increase in the gamma. Now, the important in the today's spectrometer technology is very important what type of probe you are using. So, as remember we discussed two types of probes, one is called gyromagnet RF probe, which is cryogenic cooled probes, and other is basically a room temperature probe. So, the cryogenic probes are 3 times, remember 3 times more sensitive roughly, which are operating at liquid helium gas temperatures, that is 25 Kelvin. So, there are different types of cryogenic probes, but typically a cryogenic probe means that the probe, the electronics, the RF coils and the preamplifier and other electronic parts are at a very low temperature. So, when you reduce the temperature in electronics, the thermal noise reduces. So, when you look at this S by N, the N will reduce. The sample is the same. We are comparing same sample between a normal probe and a cryogenic probe. The sample is same, but the noise will reduce in a cryogenic probe. So, as a result, the signal to noise goes up. So, signal to noise can be increased by using the special cryogenic probes. And this is typically used for biomolecules. When you look at biomolecules, we look at very high magnetic field. In biomolecules, sensitivity is a major important critical issue. So, anything which boosts the sensitivity is welcome in a cryogenic probe, in a biomolecular study by NMR. So, in biomolecules when we study, typically the studies involve using cryogenic probes in combination with high magnetic field. So, this is the combination used for high biomolecules, and that determines the sensitivity increase. So, now the most important again parameter from a spectroscopy's practical point of view is a measurement time. That means, if you record a NMR experiment twice the measurement time, how much does the sensitivity improve and signal to noise improve? The signal to noise is proportional to the square root of measurement time, and this square root is coming because of this what I discussed in the previous slide, that when you increase the number of scans, your signal increases proportionately, but the noise increases only by square root of scans. So, when you take the ratio of signal to noise, this is proportional to the square root of the scans. Square root of scans meaning square root of time, because if I double the scans, I double the time. If I increase the scans by 10 times, I increase the time by 10 times. So, time and scans are kind of directly proportional. So, if I increase the measurement time by a factor of x, my signal to noise improves by factor of square root of x. So, this is a very important parameter, because that what determines. If you want to double a sensitivity, let us say you are getting a signal to noise of 5 for a given sample and you are not happy with it. Let us say you want to improve the signal to noise to 10. That means, you want to double the signal to noise, but then you will have measurement time what you record has to increase 4 times, because only if you increase the time by 4, your signal to noise will improve by a factor of 2 based on this equation. So, you can see the time is very important, because sensitivity depends on time very critically. So, typically this is how we prepare the sample for NMR experiment. You start from basically a sample which is of this volume. So, the standard NMR spectrometers, if you are using what is called as a 5 mm probe, a standard spectrometer has, this is the volume required for preparing a particular sample, and that sample has to be prepared in a given solvent. So, based on the type of your molecule, its solubility and so on, the solvent will vary. So, typically if you are looking at biomolecules like proteins or carbohydrates or nucleic acids, we use the standard solvent, that is aqueous medium, which is H2O, and sometimes you put it also in D2O, heavy water, which is an isotope of proton. Sometimes you require for certain reasons, we will see that later. So, these are the two, both are aqueous kind of solvents. Now, for organic compounds which are not soluble in water, you can use different other solvents such as chloroform, deuterated chloroform, CdCl3, which is the most popular solvent in organic chemistry, or you can use DMSO. DMSO is another organic solvent which is used for looking at molecules which are not soluble in water. So, similarly there are many varieties of other solvents like methanol and so on, and all depends on the type of experiment. And the solvent, one important point which we will see little later on is that it is important to have the deuterium nucleus in your sample. So, if you remember, we looked at the hardware aspects, there we saw that the magnetic field continuously drifts, means it reduces in the frequency. This is something which we cannot avoid. This is the basic aspects is inherent in the magnetic field, and therefore, during the course of the experiment, as long as you are doing the experiment, you want the correction for the drift. You do not want to allow the drift. I mean, drift will continue to happen, but you want the system to not see the drift, and if you want to do that, you have to do a correction, and that is done by this concept of locking, and the locking basically compensates for this drift. So, what is done is typically that you take a nucleus which is kind of inert or which is in the background, and that you add a small amount of your deuterium, need not be D2O, remember it can be also D here. You can see in CdCl3 also you have a deuterium. So, you just need a presence of a deuterium nucleus in your sample, not in your molecule. It has to be in the solvent, it can be in the solvent, because the molecule then will have a different frequency of D. So, typically the solvent deuterium is taken, and that what you do is you adjust the frequency of the spectrometer by continuously monitoring the deuterium. Deuterium signal starts moving. Remember, you do not see the deuterium signal yourself, it is happening in the background. So, the deuterium signal is continuously monitored by the hardware, and as the molecule, as a drift takes place, this deuterium value is corrected. I mean, the signal is corrected based on the signal of the deuterium, and the magnetic field is continuously kept at the same value at the as the sample experiment proceeds. So, therefore, the locking is a very important concept. One has to have a deuterium amount. So, that is called deuterium locking. So, typically if you look at the biomolecules, again when you look at biological systems, what we do is we typically take the solvent in 90% of H2O and a few 95, typically nowadays we use 95%, and about 5% D2O is added, and so that the D2O which is in that sample can be in the solvent can be used for this locking. The next important point is that we have to use a reference compound. So, the reference compound again depends on your sample. So, for organic molecules, when we take CdCl3, maybe that standard compound is reference is used as tetramethylsilane, that is called TMS. This is what we use. Remember, the chemical shift is for referencing only, and referencing in NMR is sort of an arbitrary thing, because you just force a peak to be 0. That is, if you record a spectrum of TMS, you force that to be 0, and with respect to that, all the other molecules are reference. For biological molecules, we use another compound for referencing known as DSS. So, there are about 3 or 4 standard reference molecules which are used for variety of studies. And a very important point here is that the molecule should be completely soluble in the solvent. You should not have particulate matter floating around in the sample, because that disturbs the magnetic field around the sample molecule. So, therefore, it is very important that your molecule is completely soluble in the water. So, with this we will go to the next class, where we will look at how the experiments are practically recorded and what are the different parameters we should choose to get a 1D NMR spectrum.